Let's jump right in. There's this beautiful, honestly kind of fragile intersection between the rigid logic of code and the visual art of typography. Today, in this explainer, we're diving straight into how to tame it, specifically using Haskell. We're looking at the notoriously tricky world of CJK character widths and exactly how developers can force wild, unruly text layouts into perfect geometric submission. If you've ever dealt with typesetting mixed language documents, you absolutely know the pain. So let's get into it. What actually ruins a perfectly good text layout? I mean, picture reading a beautifully formatted document. It's a uniform grid, highly satisfying to the eye. It's literally like a perfectly played game of Tetris, where every single block is nestled exactly into its rightful spot. But then, right in the middle of a flowing sentence, a character completely the wrong size just drops in. Boom. It shatters the illusion. Your eye catches on it immediately, right? So why does that happen? What fundamentally breaks under the hood to cause that jarring visual hiccup?
Okay, let's dive into this. The root cause of this layout destruction usually boils down to a fundamental clash of widths. You've got your half-width characters, standard alphanumeric marks, trying to share space with full-width characters that demand an exact, unforgiving square space on the grid. It's like trying to force a rectangular peg into a perfectly square hole right in the middle of a tightly packed mosaic. When you blindly mix single and double-width characters in plain text, the rendering engine just gets confused. It tries to accommodate the narrower character, and because of that, your paragraph wrapping breaks entirely. That predictable, soothing rhythm of the text block, it's just lost.
When you forcefully embed standard half-width punctuation into a block of full-width text, the result is, well, it's viscerally jarring. Standard quotation marks and commas look squished, almost anemic, against the denser surrounding characters. The alignment gets completely thrown off, pulling you right out of the flow. But by swapping those half-width marks for their double-width equivalents, we restore that beautiful, uniform paragraph wrap. Every single character, whether it's a letter or a comma, claims its perfect, predictable square. The layout breathes again. It goes from looking like a chaotic, unedited draft to a professionally typeset page. And this brilliantly illustrates that it isn't just punctuation breaking the grid. Alphanumeric characters are just as guilty. If you drop raw, half-width text like GPU or 95% into a block of Chinese text, the visual rhythm stutters. Those letters and numbers clump together, disrupting the monospaced flow. But convert those into full-width alphanumerics and they stretch out beautifully. They expand their shoulders, so to speak, aligning perfectly with the surrounding grid. The visual weight becomes balanced. It's incredibly satisfying to watch a previously broken line snap back into a flawless block of text just by fixing the width of a few stray numbers. Now, solving this isn't always a binary process. The author is actually actively contemplating an alternative, almost artistic approach here. Instead of a direct conversion where you alter the character itself, you could simply pad a single-width character with a half-width space. Mathematically, it simulates the exact footprint of a double-width character, but visually, it creates a layout that feels noticeably thinner and more spacious. It's a fantastic aesthetic choice that adds some real depth to the problem-solving journey. It gives developers the flexibility to choose not just what aligns correctly, but what actually feels better for the reader, depending on the context. So how do we actually automate this visually satisfying fix? Doing this by hand across thousands of lines of text would be an absolute nightmare. Let's switch from typography to the technical mechanics. To execute a comprehensive conversion across an entire document, a specific command line tool is used, the --tidy flag. Think of it as an automated, highly caffeinated proofreader that relentlessly hunts down those grid-breaking characters and effortlessly snaps them into their double-width forms. It normalizes everything, taking all the manual labor out of the equation and turning a massive formatting headache into a single keystroke. But building this tidy function introduces a classic technical hurdle. The core workhorse we want to use for the heavy lifting is t.replace. The catch? Well, the t.replace function naturally expects two separate arguments, the string defined and the string to replace it with. Because we have a massive dictionary of these pairs to process, every letter, every number, every punctuation mark, we absolutely need a way to pass our lookup values efficiently. If we don't, our code is going to turn into a sprawling, unreadable mess of repetitive replacement commands. Now, what's really interesting about this slide is seeing exactly where Haskell's functional elegance shines. You could use a lambda, an anonymous function, to manually unpack those variables. It certainly gets the job done, but it's verbose, it's clunky, it feels like brute force. Instead, we can visually contrast that against the elegant uncurry adaptation. Uncurry beautifully adapts t.replace to accept a single tuple, neatly bundling our find and replace values together perfectly for the fold operation. It's incredibly clean problem solving that takes a syntax that could have been noisy and distills it into something highly readable.
So the crucial point is how you actually define that massive mapping list in the first place. You have choices here. You could use Unicode escape sequences, which are mathematically precise, but honestly, a total nightmare to read. You'd just be staring at strings of hex codes trying to figure out if it's a comma or a bracket. Instead, the author made the brilliant choice to use literal characters directly in the source code for their single width to double width mapping. You get immediate visual feedback right in your text editor. You literally see the half-width bracket turning into the full-width bracket in the code itself, completely bridging the gap between the programming logic and the final result.
It's incredibly detailed, granular work. But as the author, Ang, puts it, handling these quirky little text manipulations is honestly half the fun. When you've been working on typesetting for text to ebooks for a while, this isn't a frustrating chore. It's a real geeky passion. You are sculpting text. And, with a little AI assistance to unearth the right functions or track down obscure Unicode blocks, solving these layout issues becomes a deeply satisfying part of the process. It's that beautiful moment when the grid finally locks together.
It's just a wonderful reminder of the hidden joy in problem solving. It's about taking a system that wants to break and engineering it into something beautifully resilient. As we wrap up this explainer, I want to leave you with a question to reflect on for your own work. How will you tame the quirky little manipulations in your next project? Will you just muscle through it with brute force, or will you find your own elegant, perfectly aligned solutions? Thanks for exploring this technical, typographic journey with us, and definitely take a closer look at the text grids around you today.